Okay, without further ado, we're going into lecture 2.1. Our first section of this week is about search. Now, many of you probably already kind of know, but search is a sort of a big portion of AI. If you really think about decision making or any kind of intelligent system that wants to accomplish some kind of objective, and say it has the ability to search every possibility that exists of things that may not happen based on actions and different options. Well, if you have that, it may be a massive search space. It may be literally the entire universe of search spaces. But if you have an ability to search through that efficiently, then you can make a decision based on that search. Like one of the really classic examples here is chess, right? If I could just, given a particular state of the board, and given all possible combinations of actions, right, if I can search that entire tree, then awesome, right? Now I can determine which move to make based on the best expected outcome of that, right? Of varying depths of search. Now, if you have a full search, and if you can actually search the entire tree, like imagine a game like tic-tac-toe, this isn't actually that absurd, right? You can go tic-tac-toe in only so many combinations. I think it's like 10 to the 10 or 20 or something, I forget. But a game like chess is significantly bigger. A game like chess is in the order of 10 to the power of like 120 or something. I forget exactly the order of magnitude, but it's so big that we don't have computers that could calculate that, and so that's why it's not really possible. This fits into, if anyone's interested, into the concept of also what's called Kolmogorov complexity, and just generally speaking, right, this say you have a byte stream that's coming in, and you can kind of try to guess what's producing that byte stream. If you can reproduce the program that's producing that, then you understand the underlying structure of that data, and one of the ways that you could in theory do this is search through different algorithms that are producing data, and if you can search through all of them, you'll eventually find the one that's producing that particular stream, and this is related to the complexity of that. So it's very an interesting and deep subject, and for anyone who's really interested in going even deeper on this, really recommend checking out Marvin Minsky's kind of seminal paper on artificial intelligence that really digs into sort of the multiple components of what is intelligence, what is artificial intelligence, and search is the first one. Right. There's a lot of things that we're going to be searching. We're going to be searching, for example, navigation of a space, but how is that encoded? We're going to maybe do pattern matching. We're going to have to make decisions under uncertainty, and we're going to have to sort of then plan as well. So artificial intelligence kind of breaks down into these four quadrants if you really kind of dig into it. But search is the first one because, again, it kind of comes back to that fundamental I mentioned in the beginning. If you have a set of options and it's a finite set of options, searching through those options is kind of critical to you being able to determine what to do. And actually, there's a lot of evidence that this is what the brain does using the hippocampus, where we use our hippocampus to sort of navigate our thoughts, literally in the same way that we navigate our environment, using things like grid cells and place cells, and it's a pretty interesting subject. So anyways, let's dig into search. As you can hear, it's something that's really deep. I'm sure a lot of you have bumped into it at some point in the last few years of studying, so a lot of these things won't be that out there. So, a lot of search techniques have sort of a worst case complexity, right? Like, for example, merge sort is O log n in that, and so on. You kind of have these different, like if you're doing a binary tree and things like that. So even with that, right, you're still bound to n, and if your n is quite large, this may take too long. And if we're talking about in the context of AI and game development, real time actually really matters, right? So, there's a lot of possible game paths, as I was mentioning. This number actually I think feels very small to me. It's 10 to the power of 120, not 10 to 120. So apologies for that thing. But yeah, chess has 10 to the power of 120 game paths, and checkers has 10 to the power of 40 game paths, and something like tic-tac-toe has significantly less, like 10 to the 10 or something like that. But these are massive numbers, right? There's no way for you to search through all of those possible combinations of moves and so on, especially when you're at the top of the tree, which is what's my first move gonna be. So it's very difficult to determine what's the best first move, because that's depending on all of the possible ways that the game could go from that point, which happens to be of the order of magnitude of 120, which is quite huge. So more common, you see two-player games with trees. Like even in games like chess, you don't necessarily create a tree for the whole game. You create a game tree from the current point, and then you kind of go to a particular depth, and that way you can kind of go and explore what is the best combination within a given depth. And so tic-tac-toe, as I mentioned, this is a really often used to talk about brute force, because it is a much more limited game than something like chess. So yeah, 10 to the power 120. Sorry, there's a formatting error there. I didn't catch that when I was changing the slides, but it's 10 to the power 120 is comparable to the number of molecules in the universe. It's a really like massive number, and I think it kind of this sort of digs in at the surface a bit of like why intelligence is such a hard problem, because the space of the complexity of the space that intelligence has to operate in versus say like a photon bouncing around is just massive, right? Because it's not dealing with these events that are kind of fundamental and contained and bound. Artificial or intelligence in general has to deal with the possibilities of events, and yeah, so it's a very it's strange. It's like almost like the quantum physics or the dark matter of computer science in a way. Is how do you really build an intelligent machine? That's why it's been an open question for a very long time. So yeah, the one way that you can kind of approach this problem is, as we mentioned, like say you're doing a game tree, you only go to a certain depth. You can also sort of minimize the branching factor, and so you can kind of prune trees down and say, oh, I'm going to only search in these directions. There's actually a technique called beam search that's particularly popular in like natural language processing, and what it does to determine what the next word should be, you have these probabilities of what the next word should be. Imagine having like a hidden Markov model or some kind of probabilistic language model, right? But what happens is you have these nodes that down the line may be more likely, but you might be going down a path that is less likely. For example, I have a model that is saying I am the, well, let's just say I am, right? And then the next word, the most likely word is the, but after that, the next most likely word is the, because that's the most common word in our, dictionary, in our corpus. And so if you just do a brute force search, you're just going to keep on I am the forever. But if you have a search instead that, okay, we'll sample the, and we'll sample the next two most likely examples. So I'm going to be I am the, I am, a, I am, some name, like I am John, right? And then you keep doing that, and for each one you take the most likely, but then you also sample the other ones, and you can eventually get to a conditional probability likelihood that is greater by finding these sort of other paths that are more likely. So I am the is less likely overall than I am John. Period, right? And the end of the sentence is also a token. So anyways, there's a lot of techniques here that you can use to prune the tree, to say, oh, these are, like for example, in chess, there are a lot of things that just would never happen, or the likelihood of them are very low, and so you don't even have to go down those paths and things like that. And yeah, for example, with tic-tac-toe, you have symmetries that you can leverage, and then I think often this is one of the things that you're trying to do is you distill the problem down to an invariant form, meaning you try to remove all of the different symmetries to reduce the search space. So pretty cool. So this is a quote from Newell and Simon. Intelligence for a system with limited processing resources consists in making wise choices of what to do next. I think this is a pretty good, concise statement, right? Ultimately, this sort of again goes back to the subject of decision making under uncertainty. Because of your limited resources, processing, memory, or otherwise, making decisions is always done with a lack of something, right? So in a game like chess, if we're talking about heuristic search, the reason that we have limited processing, and that limits us from being able to explore every possibility in a finite window of time, or a given window of time. But in some cases, it's not even the performance that we have access to, but it's also just the incompleteness of the game. Like, for example, think about StarCraft or a game that has a fog where you can't actually see what your enemy is doing until you get there. And this is sort of what's called an incomplete game. I'm not really deep on game theory, but it's interesting. There's some really cool things to dig into there in game theory about what's the optimal decision making to make in a incomplete game scenario versus a complete game where you have complete information. So let's kind of explore these two realms. We've already been talking about chess, but there's a lot of other places in the world where you can have to make decisions under uncertainty in medical diagnosis or medical, like prescribing a drug or deciding on what kind of medical procedure to make. Essentially, you can sort of think about that as there's a likelihood that you'll succeed, and there's going to be a bunch of different options. So which choice do you make? So for some problems, you may not have an exact solution, right? Because there's just no way to have complete information. A medical diagnosis is a really good example of this. Again, incomplete game, right? But also a very, very complex system, the human body. And so you can say, well, we have three different methods to deal with this situation, and you may choose one that it's because it's the highest likelihood, you've got 90% chance, but say you have some information about the patient, you want to kind of take that into consideration, like how do you do that? And so this is something where you might want to bring in a heuristic to determine what the next what the next choice is, because these you need some additional layer of sort of decision making on top of just the most likely thing. Like, for example, right, a child comes in to the doctor's office and they sprained their ankle, right? And the thing that worked very well for the major population was to put on to not put on a cast, to do nothing, and to just give them a shit ton of Tylenol or some pain medication. But you give them the pain medication at the scale that you would give to an adult, and obviously that's very dangerous for a child. But that just because less children get sprained their ankles like that than adults do, doesn't mean you should apply a heuristic. Like, wait a minute, like this is a smaller child, their body size is different. Maybe they shouldn't be exposed to these drugs, and instead we should use a cast. And this is again kind of an example of we have knowledge about the situation, and let's leverage that in a heuristic fashion. In other places, that there is an exact solution. For example, a game like chess where the rules are artificial in of themselves, right? There's very discrete rules. There's no continuous action space. You either move your piece or you don't. It's your turn. It's either your turn or the other person's turn. It's a very kind of known state, and it's also a completely known system. Like, you know exactly where all the pieces are. You have no different information in your head than your opponent does. And in that kind of scenario, it's all about just trying to kind of make efficient use of the available computation, which is a very inhuman thing, which is why it's a human sport, right? But it's a funny thing to say that human beings are actually really bad at these kinds of things, but they're actually much better at the first, which is why you find a lot of sports and games in the latter category A lot of people actually see that, you know, machines and AI are able to solve these games, and we're like, oh no, like machines are taking over. But the truth is, the reason we all glorify these games like chess and so on is because it's an inhuman thing to do. We're like fundamentally bad at this kind of computation, but we're very, very good at this sort of like, you know, causal Bayesian decision making that machines are extremely bad at. So just an interesting thing. If it's easy for you to do, it's usually really hard for a computer. If it's really hard for you to do, it's probably very easy for a computer, which is kind of an interesting thing to be said about driving, but that's a whole different story. So one of the problems with heuristics is it's kind of the product of what you design. So human beings are very like bad at sort of explaining and talking through their decision-making process. And the codification of those heuristics are often not a full translation, right? Like when you talk to somebody and you're trying to assess their knowledge about a subject, you use everything from their body language to the terms that they chose to, you know, you're biased. You can see how tall they are, what they look like, and how they're behaving, and how confident they are, and often will think somebody is a total genius when in fact they know nothing about the subject, and vice versa. And so we actually taking that and like trying to turn that into a test, for example, right? Like often a test will not be very accurate in terms of determining your knowledge on a subject, because you sort of try to convert your own, this biased, very, very biased, like, oh, this is the questions I would ask somebody. But the reality is you're assessing their intelligence in a very different, that's a very bad example, but the point I'm trying to make is that human beings are very bad at codifying these heuristics, things into heuristics, because our perception and observations of the world are so broad and much of it's unconscious to us, and so very often our heuristics lead to suboptimal solutions. Sometimes it works and you can prove it mathematically, and this, like things like GJK, for example, and some of the search algorithms we'll talk about, but often you you end up making an algorithm that kind of works in a local thing, but as soon as you get out there, it does not extrapolate. So going into heuristic algorithms, there's two kind of parts to them. One is the measure that you're using. So this could be many things. It could be the distance on a map between two spots or something like that. And then you also have an algorithm that actually searches that space of states. So one of the kind of examples here is hill climbing, which is a really, really good example because this is most of machine learning uses a form of this, which we won't go into in this lecture, but maybe a different one in this class. So if you think about being on a hill and you want to get to the top of the hill, it's sort of that's your goal. And so how do you get there in the fastest way possible? Well, if you're standing on the hill, you want to turn yourself to the point where you feel the steepest slope, which would also kind of to you feel like you're being pushed down the hill most aggressively, right? Because the normal of the hill is you're standing up straight, you're like this, and there's a force being pushed on you down the hill effectively. And so if you look in that direction and then move your foot in the direction the opposite that opposing force, you will be going up the hill in the steepest way, which is great, but like, well, by the way, you know, like that's not always possible physically. And sometimes this is also true in the context of optimization. In things like machine learning, where you can ensure that the hill is nice and smooth, it's no problem. But there are certain problems, and in particular games and heuristic-based approaches deal with this. You may not have there may be discontinuities. You can kind of imagine there might be an overhang. So going in the steepest way, you might bump into a place where you can no longer make any progress. So that's kind of an interesting thing. So there's a lot of things that can go wrong. One issue is, say you're on a very bumpy hill, right? And you go up to the top of the hill because you're following the steepest ascent, but then you get to this top and then you look over yonder and you actually see a bigger hill. Now, imagine you're like an ant and you can't really see over the grass, right? You're just trying to climb up the hill. and you get up to the top of the hill and you feel the steepness. You're like, I'm on top. But in reality, if you zoomed out, if you're able to see over the grass, you would see much bigger peaks other places. So what's called local maxima are problematic for hill climbing strategies, right? Just like you have that discontinuity like a cliff, you can get stuck that way. You can also get stuck by being in this sort of local region where there's you cannot make any progress anymore with this strategy because you're at the top. If you take a step in any direction, you'd be going downhill, right? But you would need to go downhill to see the next, better slope. There are actually a lot of techniques to deal with this, because this in machine learning is actually a really big problem. But so one of the techniques, actually, I'll talk about really quickly here, is what's called the rolling ball or momentum. So imagine you're like Sonic the Hedgehog, right? And you're going really fast, and you have some momentum, and you go up the hill. And as you're going, you're kind of slowing down, but you still have some momentum. So when you get to the peak, right, you kind of overshoot it. You overshoot the peak, and you keep going a little bit. And then you kind of reassess. You're like, oh, wait a minute, like the peak is that way. And so you're still kind of like stopping down the hill. But then all of a sudden you hit this like gully or a saddle point of some kind. And you say, wait a minute, I'm no longer going that way. I'm going this way because there's a bigger, better hill this way. So just adding a momentum element, which is essentially a exponential moving average, can often avoid this problem entirely, which is a really, really valuable thing to know about, both for machine learning, but also if you're doing this kind of hill climbing strategy. So yeah, what's one thing that we can do in search is something that a lot of you have heard already about. Pathfinding techniques, for example, Dijkstra's and A*, which we'll talk about in this lecture, are really good for searching spaces in particular. Now, when you're talking about A*, or in the case of Dijkstra's, there is no notion of a heuristic, right? Ultimately, you have the notion of these nodes and the cost and the visited, not visited, and all that fun stuff. And in a way, that's great because, now you've got this sort of general purpose algorithm that can just explore these things. But we're making games, right? And we're trying to explore, let's say, a space. We're trying to navigate a path or something like that. And so if you can layer a heuristic on top of this, then you can make this a little bit better, right? Say we were in a grid world, and we know where we want to go, and we just explore all the nodes next to us, and kind of keep on expanding out that search. But we also know that the goal is like over there. So why do we even care about the nodes behind us or that are in the different direction? And maybe there's a boundary and there are some issues there, right? So we'll keep going in that direction. We'll hit a wall, and then we'll start to explore the ones behind us to compensate for that heuristic being wrong, because the heuristic is saying go northwest, and then we go northwest, we hit like a wall, and so like, okay, I guess we had to go southeast and then up and then left. So this is a problem with things like A* sometimes, but it's still on average much better than Dijkstra's. We'll talk a lot about this, but many of you, I'm sure, have kind of an experience with this if you're playing games like RPGs or something, or not maybe RPGs like Valheim or these kind of open world games where you're fighting an enemy, and you find this really funky little spot in the world where if you go slightly to the left, the enemy has to kind of go all the way around the other way. If you go slightly to the right, the enemy has to go all the way the other way, right? And that's because you found this sort of spot in this algorithm that's telling A* to explore these different paths because of this. It tries to go at you directly, but there's this big thing in the way, right? And as soon as you go to the right, it's like, oh, the shortest path is actually all the way, like not. It kind of tricks the algorithm. There are better techniques, by the way. I won't talk about them too much, but if you're interested, there's an algorithm called Jump Point Search and Jump Point Search Plus. And what these do is they're very similar to A*, but they kind of project out in a particular direction. They're like, we're going this way. Let's not even check the other nodes. Let's just keep going in that one direction until we hit something and reassess. And that's why it's called Jump Point, because you go from where you are and you jump. and then you reassess kind of the nodes that you've explored relative to the heuristic, and you kind of do it that way. And on the expectation, it's actually it's just as good as A-star in terms of its accuracy, but it's like an order of magnitude, with the caveat that it has to work in a grid. It only works with a grid, whereas A-star is not limited to grids. Anyways, so let's talk a little bit about this problem-specific searches. So you can imagine a straight path with a random bounce. So we keep going, and then we bounce randomly, maybe eventually hit something. By the way, like that is like path tracing, right? Like, so it's not something that it sounds silly, but it does get used fair often. And sometimes in general, like it's for something you want to kind of behave a little bit stochastically and randomly, it doesn't work so badly, especially if you're not really aiming for a particular point, and you can sort of say, oh, I want to kind of go in a region. There's actually a really cool technique in reinforcement learning that can be leveraged here. So instead of having one grid mesh, what you can do is you can actually have multiple tiled grid meshes. And what's nice about this is you don't need to have a lot of them. You can have a very coarse grid, and you layer multiple layers of these, and they're offset just by a little bit. And then you can run these out like a random path with a random bounce on all of them simultaneously. And because of the overlap of the things, because, right, like think about it, the search complexity of something like this is going to be, n squared, and where n is the divisions, the lengthwise or widthwise divisions. So if you have few of those, say you take your entire world and you split it up into a 4x4 thing, but then you create 10 tiles which are offset by a little bit, you're basically just adding 10 times, 4x4 or whatever, which is much better than if you go from 4x4 to 5x5, you're going from 16 to 25, and that's already a multiple of 9. And so here, actually, you add 10 more tiles, but you actually get significantly more accuracy and resolution. So it's kind of comparable to adding one more tile, but actually now I can take all of these tiles and overlap them based on the sort of offset. I could have now taken each tile and turned it into 10 by 10 little spots. So I can do this overlap, and I've gotten 10 times the resolution, but with only 10 times the slowdown. Whereas when I add one more, width-wise separation, I'm not getting that much more resolution, but I'm increasing my computation by 10 times, or essentially 10 times. It's a little bit less, but anyways. So surprisingly effective, this little thing, if you do some cool stuff. Although reinforcement learning doesn't really use that tile coding anymore. They just use neural networks to encode the space into a sort of abstract thing. And then wall following. So if anybody's ever been in like a corn maze, and you know about the right-hand rule, or just always go right. Just like stick to the wall and go right, and eventually you'll get out of the maze. Because if you just do that, you're always guaranteed to search and find not the shortest path in the maze, obviously, but you will find the way out. So unless there are like a loop where you're going right, and you get stuck in this loop. But if there isn't, so you have to be a little bit not stupid, right? So if you're like going right, and then you come out, you just keep following this pillar. So you have to be a little bit smart. Let me just take one break right now to get a little bit of water. I'll just be pausing, and it'll come back as soon as I say this. Okay, so let's talk a little bit about a kind of search algorithm. A-star follows this, Dijkstra's follows this, but let's call it a best first search. And the idea being that we're kind of avoiding these local maxima by backtracking, meaning we may get to an optimum, but we may not use that because we have sets that we're exploring that are going to tell us, wait a minute, this path has a better possible outcome. So the way this works, and this, if you're familiar with Dijkstra's or A-star, this should be kind of a review for you. We basically have this open list. So it tells us what nodes we've explored or haven't explored. So You start off, say you have a grid, and then the grid, you're in the middle, and your open list is literally everything except for the node that you're at, right? And you have a node in there, by the way, that is your target, assuming that you know that. This is kind of one of the expectations. You know where you're going. You can't just be like, explore it and find the thing that you don't know where it is. So just some knowledge about that. But you have this open list of all the nodes that you haven't explored yet. And you know their proximity to you based on the graph structure or the grid structure, what have you. And then you have a closed list. And the closed list keeps tracks of the nodes or the states or whatever that you've already visited. And what you're doing is you're ordering the states based on their closeness to the goal. The closeness doesn't necessarily need to be the heuristic, right? It could also be a cost of some kind. So like every node or every square in the grid may have some cost associated with it. You can kind of imagine this, or there's a nice intuition here of, say you're in a dungeon, right? And there's a big oil puddle in the middle of the room, right? And going through the oil puddle slows you down, so you might want to go around the oil puddle, right? Even though there's a faster distance through the oil puddle, there's a cost. Say the cost of a normal square is 1, and the cost of being in the oil puddle is 2, and so it's actually cheaper to go around the oil puddle versus going through it. So this heuristic will essentially be used to order the node, and this is a very kind of intuitive thing if you think about it in a grid, right? If I'm in a grid, going 1 to the left is 1. Going 2 to the left is 2, right? And so from each node, I can just add 1 to my current value, and I can add it up and just save that in the literal states and then order a list based on which node is the cheapest, right? So that's kind of cool. And then for something like A*, which we'll talk about, you order your search based on a general heuristic on top of that. So that's really it. If you've looked at Dijkstra's is literally this, right? You have an open list and a closed list, and then you order the thing, and you keep on rinsing and repeating until you get to your node, or there's no nodes left, right? And if there's no nodes left, there's no path, so there's no way to get there. And if you get to the node that you're seeking, you win. You win the game. So yeah, one comment is this amounts to a priority queue. If you want to put a name on the type of data structure that we're using, is we have a queue that's ordered not based on how the items are being added to it, but by the value, by some value, and that value is like a priority of some kind. So when the frontier of a search is uneven, best first search can work quite well. I mean, this kind of like makes sense, because if the search is like just a circle, then it doesn't really matter. Like if you could be in anywhere within a radius, the best thing to do is just check the circle going out from you, if you have no information about what you're looking for. But if you're going for a particular direction and point in space that you kind of know about, it's almost like a beam. This works best because you have this priority of items that you can say, oh, we're always closer, until you're not. So admissibility is essentially that heuristics they find the shortest path to a goal whenever it exists. Sorry, I just slaughtered this. So whenever a heuristic can find the shortest path to a node, then that heuristic sorry, I'm having a moment here. One moment. Let me get some water. Okay, I'm just gonna literally read this. So, heuristics that find the shortest path to a goal when it exists are admissible, right? So, breadth first search is admissible because it examines all the possible states before it goes on to the next level. You can imagine heuristics or algorithms that do not do this, right? Like you just go left all the time. Like jump point search, for example, is usually not that admissible, for example. But it works better in practice, so it's like a this or that thing. So let's say that we have an evaluation function for our search, and the evaluation function is how we evaluate the quality of the node that we're trying to go to, or the current path. And the actual length of the path from any state this function is composed out of these two things. It's composed out of the actual physical length, or in this case we're in a grid. Again, I think I need to really root us in that, because if we're not in a grid, then there's some kind of graph structure underneath that has on the edges these distances, and then on top of that we have an estimated distance from the state, that current node to the goal. So this is, by the way, why A star, this is A star and not Dijkstra's, because Dijkstra's doesn't have a notion of where the goal is in a distance, right? This distance is a layer above our data structure. And so we can represent this function as g of n plus h of n. So n is the node in our graph, or it's in a grid. G measures the depth. So if you try to treat you can kind of do this in a memoized fashion, right? Like the node, like almost like Minesweeper. If like the nodes one distance from us are at depth 1, the ones one off of that are depth 2, and so on and so forth. And Gn is essentially just that depth, right? It's how many minimal numbers of steps or number of grid boxes away are we. And then the h of n is the distance that we estimate that is from n to the goal. So those are the two things that we're adding up here. And so f star, and this is actually pretty common in reinforcement learning too, like you'll see the star, the asterisk is sort of this designator of optimal. So the optimal path is the shortest path from the start node to the node n. So our target node is n steps away optimally, right? And then the actual cost of the shortest path from n to the goal. So this h of n should be the actual cost of that path. So I think that's the one thing that we should I think clarify here is, as you go closer, as the n gets closer, right, the path is getting closer, and so you'd think, oh, h of n should be going down, and that doesn't make sense anymore, because this number is going to get smaller as we get closer to that. And what is this h optimal thing? What's the actual cost of the shortest path from n to the goal? Well, no, this is what we're saying is that this is the estimated. So we're this far away plus some estimated thing, and that's the estimate. And so this is actually the total length of that. So I want to confirm this for a second, so I'll be right back. Okay, let me kind of fix that statement a little bit, actually. So h of n is from the node, your estimated distance to the goal, and g of n is the depth at which you are at. So f of n is actually trying to estimate the final distance from the start to the end, which is composed out of two parts. It's the distance you've already gone to get to that node, and then the distance from that node estimated to the target goal. And so in total, this number should actually converge to the goal, to the distance of the goal. And per the admissibility of this algorithm, it'll never overshoot. So f of n will never be longer than the shortest path to the goal from your given node. So I apologize for that sort of confusion there. So what's happening here is you start off, h of n is very large because you're at the beginning and you're estimating your distance. And as you get closer, h of n goes down and g of n goes up. Cool. So in any particular case, you're at an n, and there is a true value to h of n and a true value from g of n. It's kind of funny to say g optimal n because we know this is a deterministic function, but we don't know h of n, right? So we're constantly we want to know f of n, the f of optimal n, but we can't because h of n is not known to us. So we're estimating. We're always estimating f of n, and as you get closer to the goal, and when you finally do, you converge to f star of n from your starting location. So just explanation here, and I apologize for the confusion. So algorithm A, right, and we're not going to talk about it too much, but algorithm A may find a less than optimal cost to the current node. So G of n is a reasonable estimate of G star n, right, and G of n is going to be greater than or equal to G star of n. So it's sort of like, let's say you have an A algorithm. Let me just make sure that I'm explaining this one correctly as well. One moment. Okay, sorry for taking a minute there. I've actually never seen this formulation of it. I actually thought this was sort of more of a, hey, algorithm A. And then, but no, algorithm A actually is an actual algorithm, although I've never seen it used in practice. And it is a best first algorithm. And the main difference is that we just are not calculating H of n. We're not leveraging the ideal. So our estimate of f of n is just going to be equal to g of n. And the reason this works is that g of n is always, well, it's not optimal, but it'll work eventually. And the reason that's the case is because g of n is always going to be greater than or equal to the optimal g of n. And so if you search all of the nodes in your space, you're eventually going to find your optimal g of n. But your current g of n may not, like, it might go up and then left, right? And so g of n is not always going to necessarily be the best approach here. So you are guaranteed because it's a best first algorithm, you're going to eventually find your way, but you're not necessarily guaranteed a optimal cost, because you might find it in a sort of unnecessarily long path. Whereas the A star algorithm uses both the estimated algorithm, the estimated distance, and your current depth, and that allows us to get to the minimal cost, because you're constantly going in the direction of the minimum h of n. You're constantly reducing this h of n value down, and you're taking into consideration both of these. This is h of n becomes a reasonable estimate because it's guaranteed to be less than or equal to the optimal h of n. That's actually, I think, kind of the definition of A star. Like, you need to actually be able to calculate that heuristic, right? Like in a grid, that's the Manhattan distance, right? Or in a more kind of continuous space, it's just the Euclidean distance. And if you're using some funky other thing, it's the distance in that. So that's why that's the fundamental distinction between A star and A. I didn't realize A was a whole algorithm in of itself, because nobody fucking uses it. So don't ever don't use it. Cool. So all A star algorithms are admissible, and the breadth first, search is A star, right? You start off, f of n is going to be g of n plus 0, and there's no heuristic. So that's okay. Okay, fine. So here's another statement about search, like about heuristic search informedness. When one heuristic is better than another, it is more informed. And the more informed this algorithm is, the less states need to be expanded when searching, right? And this makes sense, right? If let's say our heuristic is just a direction, we may not take into consideration some distance things, right? And like, for example, okay, actually better, yeah, say we're like doing direction and we have a map, and on the map there's a big mountain on the map, right? And we say, wait a minute, like there's a mountain over there, so like we probably shouldn't go in this direction, we should go around the direction, right? And so you can kind of say, well, the algorithm that leverages that map as a heuristic is more informed than somebody with just a compass, because somebody with just a compass may not be able to see the mountain because they're in the forest or something, then they pop out, oops, there's a mountain here, I have to go around, and they're not going to get to the optimal path because they've wasted some distance. So there's a cool example of that. So what about the code? It's actually pretty simple. Like, I guess we're not really going to go into the code in this lecture, but it's essentially that visited, not visited set, and that priority queue with a few data structures, keeping track of your paths and stuff like that. So it's really not that hard to write these algorithms. Harder yet to build it in the context of like an engine and a whole thing, but for the most part, it's a pretty eloquent thing and takes up a very limited amount of code. So remember that the A star, algorithm is a heuristic search, and that's just the sum of the cost and of what it's left. So just a reminder. So the way, let's go through the algorithm itself a little bit. I'll move my head here. So the way you go through the A-star algorithm, we're not going to go through the code, but we're going to go through the algorithm. We're going to take the source node, or this is the current node that you're at, and you're going to add it to the queue of visited nodes. So this is like the first, you have empty everything. You know your starting node, you take that node, you pop it out of the open set, and you put it into the visited set. Now you start the algorithm. While the destination node has not been found and the open queue is not empty, you take the first node from the open queue, right? And if you see if it's the destination. By the way, these queues are priority queues, right? And the costs are just kind of calculated for us and based on the sort of heuristic that we've talked about. So we see if that node is the destination. If not, then we add all of the neighbors of that node into into our visited queue, or sorry, into the open queue. Sorry, I'm like mixing up the visited queue. It depends how you write this, honestly, but either way, like you take the node in the open queue at the top, you throw it away, right? You add its neighbors to this other thing, and then you go through those, and now you know which nodes to process next. And then you remove that node, and then you go through the rest of them. And again, the queue priorities are defined by this heuristic function. So, sorry, not the best explanation, but it's the general idea. You basically start at a node, you evaluate it, then if it's not the destination, if it's not good, you throw it out, you take its neighbors, you stick it into the queue, you put it into the visited queue, and then you move on. So here are some heuristics, and I think this is a good example, getting into the real meat of A-star is less about the code, but more about the heuristic that you use, right? So one is this Manhattan distance. Manhattan distance is named after basically like you're in a city like Manhattan, and streets are going, north, south, west, east. You can't go diagonally, and so you constantly have to kind of go up, down, up, down, up, down, up, down to get to where you're going. And so this way your distance is the combination, the linear combination of your y as your x difference between your goal and where you are. Again, you're in a grid, so you kind of can do the delta, as well as the y. So you just add this linearly. You don't do like Pythagorean's theorem. I have to go left and up, and that's it. So that's one thing. That distance will always be larger, right, or equal to the diagonal. And so another thing we can do instead is we can do the diagonal distance, which is going to be just the maximum of the x or y difference, right? So we can use this. And this is a good example of the heuristic not actually being very close to likely the actual distance, right? And you can sort of see here that one of the things that happens with this algorithm in the right case, where you have this sort of boundary here, is you have to go and almost like hit the wall before you realize that there's something kind of in the way. So the maximum here on the right example, the max is going to be the x for a very, very long time, until it's not, and then it's the y, and then you start going down again. So I'm not actually entirely certain what all the colors in this particular diagram mean, but the red line is the path that you ultimately take. But these boxes you still have to explore all these boxes. And I think that's one of the reasons, right? You have to kind of go left, and then you start to, wait a minute, like this would be less, and you kind of have to kind of expand it in this sort of diagonal direction, because you get close, eventually you hit the wall. And the reason you do that is because the x is what's driving you. And so that's you can kind of see you get this sort of non-optimal thing, whereas if you look at the previous slide, we have this much narrower path. We don't explore all of these states here, but then here we kind of explore everything, and it's a bit of a mess. So Oh, I'm sorry. I think I'm reading this backwards. My apologies. The green is the start and the red is the destination. So here we go in all the directions. We try to go towards the red, and so we get stuck in this cavity, and we have to figure out that none of the nodes in the cavity get us to where we want to go. Eventually, we hit this point here, and then we go through all the way. Whereas here we same thing, because we're just going to the right, and we keep on exploring all of those nodes. But we have a much wider thing because we're just dealing with one of the axes. So apologies for the mix-up there. So diagonal shortcut is, a very much more, kind of combines the best of both worlds here, right? The diagonal cost is d2, the cost of the distance without diagonals, plus the cost of the diagonal in min direction, minus the 2 squares it would have taken to go in x and y. So it's sort of like a combination of the Manhattan distance and the diagonal distance. And as you can see, it sort of marries the best of both worlds a little bit, but you still have this problem with this cavity. But I think I don't know if you can really deal with this cavity without going to something like jump point search, where you just sort of seek in that direction, and then you say, oh, there's no way to get through here. Then you kind of seek in a few other directions and realize, oops, there's a cavity here. So this is actually more common in like a continuous space. So often when you're not doing grid, but even in grid it does work, and you basically just take the diagonal distance. So you can basically take the x squared plus the y squared, take the square root of that, and you get the distance between your points. And you can see it's not bad. It's not that much worse than anything. It's a little bit, it creates a little bit of waste in some cases. So you can sort of see this is almost like the optimal one, this diagonal shortcut. It kind of uses both. So like this kind of spreads a lot. This has a very narrow, but perhaps a slightly, less stochastic kind of exploration, and this is a bit of both. So I don't know. This is it still goes in the right direction. It doesn't spread too far, but it does a little bit, which is why the real value of this in the context of A star is when you have a situation where you couldn't do just X or Y. I mean, you could, but this is much better when you have a continuous space, and the value here is not going to be an integer value, the square root of two things, because then you all of a sudden have these annoying floating points that you have to deal with. But if you're already dealing in this open space with floating point distances and so on, why not, right? Like it's going to be a little bit more general. So one of the benefits of A star, right? It's guaranteed to give you the optimal path, and it's going to be less amount of computation than just a brute force breadth first search or Dijkstra's algorithm, which both don't have a notion of a direction of a north star to follow. It's still a little bit less fast than just best first, as in every scenario. It's because it's guaranteed to show the optimal path. So like in theory you could find the not optimal path faster, right? Like with the A algorithm allegedly, but that's probably it's going to be generally, except for like very, very strange situations, not a huge difference. A star looks at a lot of positions, not all of them it needs to look at, so that's sort of one of the drawbacks. And it's not a dynamic search, so if something in the world changes, you have to do it again, right? If you say I want this character to go from here to here, and the world is static, you can almost save that search and almost even cache it in the world, which people do that sometimes. But if the world is a dynamic world where like there's a boulder and it's moving around and things like that, you're going to have to run the search every time that the world state changes, respective to the object that's trying to map that path out. You could probably already think there are ways to engineer, ways to sort of codify it, memorize it, things like that, like layer on the nav mesh an additional layer of a dynamic thing so that you can just use an underlying nav mesh, but then on top of that sort of say, well, this is the dynamic nav mesh, and sort of kind of combine them in a way. And this is something that Skyrim did, as I mentioned in the previous lecture. So why not use best first? As we talked about before, the A algorithm. Well, in an open world, I guess it would work if literally it's open and there's not much like weird walls and strange things. So if you're playing a game that doesn't actually have boundaries or things you have to navigate. But if you do, so like that's like the left example, right? If you have just this big open space, then it probably doesn't matter. But if you have a world where there are obstacles, especially obstacles that sort of have these cavities, these like concave type of things, it'll come up with very strange paths that don't really make sense because it's just being greedy. And by greedy, it's just sort of taking what's available to it immediately. It doesn't sort of wait and see what might be better. And so you can kind of see in the right example here, the path that it ultimately takes would be very strange, as it goes inside of the cavity, then back out of the cavity, and then around. Because it's not taken into consideration the cost of these alternative paths. It's not saying, oh, if I went this way from up and to the right a bit, I would actually get to my original path. And that's sort of what A star is doing. It's sort of keeping track of the best one, exploring that until it's no longer the best one, right? At a certain point in A star, you get down this path and you realize, oh, wait a minute, this node to the top right of me actually has a lower cost than me. I'm going to stop exploring this path. I'm going to go in a different way. So the initial paths all have the same cost with a diagonal distance metric. So this is true. But yeah, sometimes in A star you have a situation where multiple paths have the same cost, and oops, I'm covering this stuff again. So, you have to kind of think about like, well, what do I do when multiple paths have equal viability? And this sort of, the cost can be reduced by tie breaking, and you have to sort of come up with an algorithmic way to do that. And one way is to just add a random number. So you add a bit of stochasticity to HN, and that way you can kind of tie break randomly, and this kind of fixes the problem. One way, you can hash the coordinates, so it's sort of pseudo-random, or you can also scale the addition to be less than, one step cost min, cost of path, so like you get a little bit of optimality there. So you sort of say, you add another heuristic on top of the heuristic that is based on the number of steps that then kind of makes a certain path more desirable than another. So I guess that's not a random thing, but it's, yeah. Cool. So let's talk about IDA, and this is an algorithm I'm not as familiar with personally, but it basically takes A star, and I guess I am covering this thing. I'll go up here. It takes A star, right, and it is instead of doing a breadth first search, it does a depth first search, where the function cost starts at a minimum using the heuristic and is increased by 1 every iteration. So this is interesting in that it chooses a particular branch of the tree of your grid to search through based on a heuristic. And the cost increases every time you search. So if the cost goes up too much, then you stop and you kind of go in a different branch, which is kind of cool. So you can sort of explore different branches. Now, it can be problematic if you choose the wrong one. You can get stuck in a really bad one. Also, it has a memory limitation. It can be slow. So it will repeat a lot of states as well. So fringe search reintroduces some of the memory ideas with A star to reduce the searching of iterative depth A star. It claims it's faster by A star. I'm not familiar with this particular one either, but so I don't actually know. I've never used it. But apparently it claims that it's faster than A star by 40% because it doesn't sort the nodes, and it just kind of acts as this cache to keep. It's basically iterative depth A star, but with caching. So, it kind of, A star kind of does this, right? It keeps track of all of the memory in this prioritized queue, And so that way you can just read the queue and you know exactly where you are and where to go. But in if you use iterative depth A star, then you lose that information because you go back to the start every time. But here you can say, well, I don't need to go back all the way to the start because I can sort of, go back to the last best known location. Or you can even cache it and say, we'll go back to the start, but we'll use data we've already collected. So now you actually do have two lists. You have the fringe list, and then you also have, the non-visited, list. So again, this is a classic trade-off in like memoization, right? You're trading off memory for time, for performance. So you don't have to recalculate things that have already been calculated. Hierarchical A star, and you see this trick used in a lot of places. You instead, and I kind of talked about this a little bit in tile coding. So you can imagine using A star to run on a coarse grid, right? And then you just keep on getting finer and finer and finer until because now, okay, say I know the quadrant that the thing is in, and then it's sort of like zone, and then it's state, and then whatever. And then you can sort of do A star at each level of hierarchy, and so you're essentially telling the algorithm, do not search half the world, now do not search another half. There's a really cool space partitioning algorithm that kind of does this in a very fun way. It's called the KD tree, and it sort of splits on different axes every single time. Although, in reality, I think octrees are the ones to use, but yeah. So this is... this kind of makes intuitive sense, right? When I'm looking for something in my house, I first start by thinking, in which room is it going to be? And then once I'm in the room, I'm thinking, okay, is it in which piece of furniture might it be? And then I go to that and then in which drawer is it? And I open the drawer, and then in which part of the drawer, and then you kind of can go finer and finer and finer until you get down to photons. So, that's what I like to do on the weekend. So dynamic A star or D star. So this fixes the dynamic path issue, right? Because in the real world, the world is not static. And so if I'm in a location and I'm like, okay, I'm going to go map a path to where I'm going, right? And I'm just going to follow that path without thinking about the way that the world is changing. I might bump into people. I might bump into dogs. I might bump into other robots. Who knows? And so what you do is you just basically assume that there's unknown terrain, and you compute the shortest distance based on your current knowledge. You go in that direction, and when you hit an obstacle of some kind, you add that to your map, and then you compute the shortest distance with that obstacle in mind to the current location. So you're constantly iterating a new path every time you come across a change to the world as you know it. This is like, I know this is an algorithm, but it's kind of dumb, right? If you've ever used iRobot vacuum cleaner, right? This is what it does. It comes to you and it hits you, and then it's like, oh, there's a thing here. I'm going to turn around, and and this is like what I would define as stupid behavior. So, so yeah, it's not used very much in games, because if you saw an enemy and it bumped into a tree and then bumped into the tree again and just keeps on bumping into the same tree, you wouldn't be very happy about that AI. So it's not used in games very much, but it's very useful in simulation and in physical product, right? At the end of the day, the only way to solve that iRobot problem is to give it sensors that are capable of sensing its environment beyond its means. Because you can imagine doing this adaptively or ahead of time. So instead of bumping into the thing, I can see it change, and I can use that change, that observation, to update my map and then run the search algorithm. And now it's intelligent, right? I don't have to wait to discover the change in the environment. I can observe the change in the environment before it happens. And this is closer likely to the way we make decisions in the world. There's a very, very cool experiment you can run on yourself, by the way. It involves the kind of intersection of place cells and grid cells, which actually do something very similar to A star, if you believe it or not. They encode your position in kind of this mesh of your representation of your environment. And what's really fun about this is human beings can have this sort of proprioception that works quite well. If you stand in a place and then you walk and you say, I'm going to walk to a particular point ahead of me, and you close your eyes, you can actually hit that point quite effectively. But try this and take a Post-it note or something, put it on the ground, put it maybe 5 feet away, and then put a third one on a triangle. It's sort of like here, here, and here. So like a little triangle where this is longer than the two other sides. And now close your eyes and go to the one point, and then turn around and go to the other one. And it's a very interesting, most people will kind of hit the first point really well, but the second one, they'll kind of veer in. They'll sort of turn and be off of it. It'll be like you're in the middle of the triangle for some reason. And this is a very like predictable thing. Keep in mind, your eyes are closed. You can't, if your eyes are open, you can do it perfectly. But it sort of shows how the fusion of our senses is limited in some capacity, and how important vision is to our observation of the world, because these place cells, these grid cells, are not very good without vision. Vision is informing us of our location in the world, and also of how the world around us is changing. So very interesting. So yeah, this is some commentary about D-Star in a game. Again, like I mentioned before, it can look very stupid. Just to kind of as a commentary for the last couple of slides here, A-Star, and by the way, no search algorithm solves movement, right? The pathfinding solves only a very small problem in the overall NPC movement. So example is, think about Counter-Strike Condition Zero if you played it, and just how bad the bot movement was, and just generally in games, especially games that require a lot of human intelligence to play well, like multiplayer shooters or whatever, how rigid bots tend to feel, and how easy it is to determine whether a person is a human being or not. And that has a lot to do with like so much more than just going in a straight shot to where you're supposed to be going. So a lot of systems around navigation. Right, you have the grid mesh we've been talking about. You can do this with hex. You can do this with waypoints. You can do this with fat waypoints, which are fatter than the normal waypoints. And you can also use a nav mesh, which is literally a mesh that represents your environment. So one example of movement is string pulling. Right, it kind of makes movement look a little bit more natural because they don't turn invisible corners on this grid. Momentum is a very similar version of that. Whiskers, it's another thing that's been used a lot, and if you're ever doing, and we'll talk about perhaps simplex search type of algorithms in the future, and Minkowski sum type of stuff, you can actually use that here in a very easy way, where you just add this to your heuristic. Right, so you just say, not only am I going to search the nodes in my location, I'm also going to search all the nodes in a certain radius at any given moment, and you can sort of predict and create a kind of a keep out away from certain things, and it'll create a much more natural type of thing. Same thing with tile coding, you can do it as well. So search obviously is not just useful for pathfinding. It kept, in Counter-Strike 0, it kept bots away from the kill zones. So this is also about decision making, and also fear. The game Fear used it for its its planner. So you have to plan how things move and how to kind of integrate that, and there's a lot of really cool examples of this. So that's all for this lecture. It became a bit long. Apologies for some of the left turns in there. But yeah, search is a really, really important aspect of game AI. We just talked about A-Star here, which is largely used for a lot of nav mesh stuff, a lot of things. But just generally speaking, search can be used for everything from deciding what to do out of a set of possibilities to making decisions in an environment such as A-Star. So it's a big part of AI in general, even though these days you don't read much about like new research in search algorithms that are heuristic in nature. Often you do read about them in the context of, for example, path tracing. Like, for example, recently a lot of work has been done in the world of reservoir sampling for path tracing or restir, and being able to leverage, again, cached information about the distribution that you previously saw to allow you to not have to do it again in the future. You can imagine applying that here as well if you have a very, very fine set of decisions to make. So that's it for today, and I'll see you next time.